For the makers who lead, success isn't measured in promises. It's measured in results. At Rockwell Automation, our 24,000 employees across the globe focus every day on delivering business results for our customers. Because with every result achieved, we realize the promise of expanding human possibilities. That's why we're Rockwell. Our customers make products and deliver solutions that touch all of our lives. And they partner with us to realize measurable, consistent, and profitable business outcomes, delivering the real results they and their customers depend on. The people of Rockwell and our vast production technology portfolio make a real difference in industrial production quality, speed, and efficiency, making a difference in ramping up adequate supplies of life-saving vaccines, making a difference by helping deliver vehicles that are affordable, efficient, and safe, making a difference by engineering sustainability into every system and solution we deliver. Because at Rockwell, we believe better is possible. And the results we deliver add value for our customers every day, in every industry we serve. Our systems connect your company end to end with data-fueled insights, improving the decisions that deliver results and expanding human possibilities. Rockwell Automation. Results achieved.
Hi, everybody. My name is Nicole Belanda. I'm the Customer Advocacy Program Manager at Rockwell Automation. And today we get to talk to Paul Zimkovich from West Virginia University. His role is the Director of the Water Research Institute. And we'll be talking about a project that he's been working on for quite a while. It's a really neat one, and I'm excited to share it with you guys. So before we get into the project itself, Paul, would you be willing to just introduce yourself, give a brief background of who you are and what you do at the university?
Sure. My name is Paul Zimkovich, PhD, and I am the Director of the West Virginia Water Research Institute, located at West Virginia University. And within our center, we have a number of sub-programs. One of them, in one of our big programs, involves mineland reclamation, and also a subset of that, which is acid mine drainage treatment. Acid mine drainage is one of the major pollutants, or the major pollutants in post-mining landscapes, particularly the pre-law post-mining landscapes in the northern Appalachian, central Appalachian coal basins. So we've been working on that for a long time. And to a large extent, trying to either make it go away, reduce the footprint of acid mine drainage during the mining process. In other words, mining in such a way as not to produce acid mine drainage, and treat it in the most efficient way possible, particularly in legacy sites, and then ultimately to restore whole watersheds that have been damaged historically. We have thousands of miles of streams that have been pretty much wiped out by acid mine drainage. And so we've had a lot of success in putting together big integrated plants to acid mine drainage treatment plants to recover, help these streams recover. And so we've restored fishery and hundreds of miles of stream in the Appalachians so far. One of the things we found out when about 7 years ago, when Department of Energy issued a request for proposals around the idea of extracting rare earth minerals from coal waste. And largely what they were thinking about in those days were either coal ash or the tailings that result from coal cleaning. I worked in a lot of those materials over my career. And what I thought would be a better idea was to look directly at the acid mine drainage. Because in order to get the rare earth elements to go into solution, in other words, in order to process them and refine them, you have to get them into an aqueous solution. And so if you're talking about rock, ash, all these mineral forms, you have to grind the stuff to a very fine powder. It takes a lot of effort. You have to mine it, grind it up, and then dissolve it in some pretty strong acids and bases in order to get the rare earth elements, our target elements, into solution. And so I thought a little bit down the road here, and acid mine drainage is basically the active ingredient, sulfuric acid, that already puts the rare earth elements into solution. I checked with a few of my friends in the agencies, and they're treating acid mine drainage and also in the coal industry, and they sent me lots of samples. So we found out that, in fact, the acid mine drainage has a lot of rare earth elements in it, and again, already in solution. And so the nice thing about that is that you are starting with a feedstock that doesn't require any additional mining. In fact, it incentivizes people to treat acid mine drainage if this works, and they recover some value in the process rather than just sinking money into an environmental good thing. And at the same time, you don't need any new permits because basically you're not mining anything. And it's easy to sample too to find out where the acid mine drainage rich rare earth deposits are. You just have to go to a discharge and measure them. So that's what we've been doing for the first couple of years. And to a large extent, what we've been doing is finding a way to take the raw acid mine drainage, get the good metals separated from the metals that we don't want, things like iron and aluminum that are just junk, and at the same time produce a concentrate at these acid mine drainage sites, because there are thousands of these around the country. Get a concentrate that has the required moisture content and grade, in other words, concentration of rare earth elements, and in a shippable form, so you can take that material from every acid mine drainage site, hopefully, and ship it to a central refinery where you can then go to the process of separating the rare earths from everything else, and then start doing the individual elemental separations.
Excellent. I asked you a short question. You gave me the coolest long answer ever. Do you mind if I dig into a couple of those things a little bit? So,
By all means.
okay. So this started as a project to clean up the water, correct, from this pollutant called acid mine drainage. Can you, just for anyone who's not familiar with this industry, what causes acid mine drainage and why is it a problem?
Oh, well, so back in the mists of time, during the Pennsylvanian era, where our coal was deposited, this part of the world, the northern Appalachian Basin, was a very shallow sea. So it was a maritime setting with a lot of peat swamps and then leading out to an ocean. So it would have looked a lot like today, either the Louisiana coast line on the Gulf of Mexico, or the Eastern Carolinas. Same kind of setting, low, flat, a lot of seawater, and of course sea levels were always coming up and down again. So every couple millennia, the sea level would rise, and then that would bring in all this salt water, seawater, onto these swamps. And when that happened, the chemistry was such that the sulfate in seawater, and seawater is loaded with sulfate, in addition to sodium chloride, which might taste like salt. But anyway, so all this sulfate comes in over these swamps, which have what we call a reducing environment. Reducing environments suck the oxygen off of ions, like sulfate is sulfur oxide. A reducing environment sucks out the oxygen, and you have a sulfide, which now is out there looking for a metal to bind up with. And in these swamps, that metal was invariably iron. So you have a precipitation of iron sulfide, which we call pyrite, also called fool's gold. Now that pyrite just lays there, and the swamp is buried under sediments over the eons of time. Eventually, it's compacted and becomes a coal seam. But the coal seams themselves aren't pure coal, because they're in these river delta environments. Think of the Mississippi outlets, the Atchafalaya Basin, or the rivers along the coast in North Carolina. They're always moving back and forth. So you have these buildups of peat, which can be meters thick. And then you have a river switch course and come over that swamp and start dumping sand and clay and whatever on it. And then the sea level comes up again, or the ocean, the coastline subsides, and you keep getting layer after layer of this coal, and then the mineral matter, the shale and the sandstone, build up on top of it. And all the time, you've got this reducing environment because of the coal and the peat that's decomposing down there, and you get pyrite formation. Now, since then, all this was happening when there was no Atlantic Ocean. Right? The Atlantic Ocean since opened and then closed at least twice during that interval. And when the last time it closed, it pushed up the Appalachian Mountains. So it used to be a big flat basin looking like the Midwest, all of a sudden turned into a mountain range. And the mountain range starts wearing away over the eons of time. And as a consequence, you wind up with these coal basins and the coal seams that are basically trying to conform with the new mountain range. And so that's why you have these coal seams that are not flat anymore, but they have a dip on them. And they have different configurations due to the topography. So that's what winds up being mined. And in the process of mining, you dig up not only the coal, but all these little inner beds of rock that are in the coal seam. And so in a lot of those, that's where the pyrite is found. So the pyrite winds up in the rock associated with the coal, and sometimes a lot of it in the coal itself, but you wind up with these, in the post-mining landscape, a lot of environments like on the top of the coal seam that are just loaded with pyrite. I've seen places in underground coal mines, where these layers of pyrite can be 2 inches thick. And so after mining, all that roof falls in eventually after the coal is removed, and that winds up being in contact with water and oxygen. And once water and oxygen get in contact with pyrite, it starts dissolving and leaves you with iron and sulfuric acid.
Got it.
So
This is
if
so
you think of a
interesting.
typical stream damaged by acid mine drainage, what you mainly see is the orange iron. And that's the iron hydroxide, which is basically rust.
And it's super toxic, right? Toxic to plants, toxic to animals, even could be toxic to people if it's mixed in
Well,
with water in a water source.
Iron isn't terribly toxic in itself, but what it does is it buries the stream itself. It buries the bottom of the stream, and it indurates it. It makes it hard, and it fills up all the little cracks and crevices that the aquatic creatures need. And furthermore, you have all this acidity in there, so the pH goes down into the 3 range, which is too acid for just about any life. And so it's the combination of iron burying everything. Aluminum is toxic, and aluminum also shows up in acid mine drainage, and other metals. But those are the big ones. So it's the combination of metals plus the acidity and the physical burying of the stream that winds up causing the stream degradation.
Got it. Got it. Thank you. So this project started as an opportunity to clean up these water areas that were full of toxicity from acid mine drainage. But then you were also explaining that you kind of sniffed out a cool opportunity as well. And it's just by nature of what acid mine drainage is, it makes it easier to extract rare earth metals. Can you share with people what are rare earth elements? Like, what is that?
Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium.
And why are those so important to us? I'm giving you a little softball question. Where might we find some of these elements?
Okay. The Department of Energy and the U.S. Geological Survey, in their wisdom, have declared that the rare earth elements, for all intents and purposes, are the ones that I just named, plus 2 that are not really lanthanides. One is scandium, and the other is yttrium. And as you know from the periodic table, directly above lanthanum, as you move up, are yttrium and then scandium. So they have outer shell configurations that kind of behave like rare earths. But to answer your question, rare earths are useful because they are capable of, because of their electron configuration, of making really powerful magnets in very small spaces. So if you have something portable like an iPhone, right, and you want things like speakers, buzzers, vibrating things that let you know when you're getting a call, those require magnets. And those magnets are invariably made out of rare earth elements, neodymium and praseodymium in most cases. And so you can miniaturize electronics very effectively by using these tiny magnets. If this had an iron magnet that did what a neodymium praseodymium magnet does, it would probably be the size of a brick.
Got it. Got it.
Not that portable.
So I'm sure demand for these has been going way, way up because all technology, it seems like, is getting smaller and smaller and smaller generally over time. So it's awesome that we can start to find some of this, right here in the US, and at the same time, cleaning up water that needs to be treated.
Mm-hmm.
can you explain a little more, why is it easier to get rare earth elements out of acid mine drainage than it would be if we were just to try to mine for them on our own?
Well, most of the rare earth in the world does come from mining right now, but it's a really long, complicated process, particularly in developed countries. So in the United States, in order to get a new, what we call a hard rock mine, so there are two kind of mines. There are the coal mines, and then there are the hard rock mines, and then there are also quarries, but we won't talk about those. The hard rock mines are the ones that are not coal. So let's put those aside and look at a hard rock mine, which is invariably some sort of volcanic intrusion that separates out valuable minerals in one part of the deposit or another. This is a science unto itself. In order to develop, and for example, copper mines, zinc mines, so forth, manganese mines are invariably, they're hard rock mines. So in order to, and oftentimes they're sulfides deposits too, but in order to get these things developed, first thing you have to do if you find a deposit or a prospect, you have to get a permit to do a drilling program. And the drilling program allows you to bore into sometimes hundreds or 1,000 feet into the ground to find out what that ore body looks like, because they're not like coal seams where you have a bed of coal that's more or less contiguous. You can have little veins going this way and that way and so forth with your goodies in them, and they can be separated by a lot of what we call gang mineral, aluminosilicate rocks, granites, you name it, things that aren't valuable. So you have to do this elaborate drilling program, drilling in from all different directions to find out how much value there is in a particular hard rock deposit. You have to put roads in, get drill rigs on the site, permits, water quality permits, you name it. That's not cheap. So that costs a lot of money. You have to take these samples out and then analyze them, determine their grade, and so forth. The next thing you then have to do, if you determine that you have enough mineral there to make a economically attractive prospect, then the next thing you have to do is get a permit. So if you're on public lands, that may involve several agencies. It may involve the Bureau of Land Management, the Forest Service, you name it, or you have private mineral holdings. But at any rate, you have to get a lot of permits, which, and if you're on a fishery, for example, or even a salmon fishery that connects to the ocean, this can be a really extensive process. There was a mine in Alaska called the Pebble Mine. It was a copper mine, and after, I think, I could be wrong here, but I think after about 10 years and something like several $100 million, the developer just gave up because they never got a permit for it. So you can invest a lot of money finding out what's there and a lot of time in developing the permits and then lining up the financing and everything else, and still get a big no at the end of it, the whole process. So that's a lot of risk. On the other hand, the benefit there with a hard rock mine is you have the whole deposit under your control. So you can maybe plot out 15 square miles of land, and that's your entire reserve base right there. On the other hand, with acid mine drainage, there are hundreds and hundreds of little sites, some big, some small, but it's basically a distributed supply chain. And so one of the things we've spent a lot of time doing is developing a process so that people treating acid mine drainage in large sites and small sites can collect and produce a concentrate of adequate grade, which means rare earth concentration, and also moisture content that can be economically trucked to a central facility for refining.
Very cool. Yeah. So I love that we're able to use this process at more than one site. Like, it's kind of mobile almost in a way. That's really cool. And it cuts out all that risk that you outlined. It sounds like it's a win-win-win-win-win, right? Like, we're cleaning up rivers, but we're also able to extract rare earth elements along the way. Where do you see this project going next?
A couple of years ago, the Department of Energy, which is our main supporting agency in the federal government, and they're responsible for this whole momentum. That's, as far as I'm concerned, it's been a really, really good strategy on their part. I've never seen any technology development move this quickly, from scratch to the point we are right now in just 5 years. This is really unprecedented. So really good strategic management on DOE's part. But one of the things they did about 3 years ago is, in addition to the rare earth elements, because federal policy regarding critical minerals, and we make that distinction between the rare earths, all of the rare earths are considered critical, or various agencies' definitions. But in addition, there are a number of critical minerals that the U.S. government recognizes that are critical because they're not mined, they're not developed in the United States. So we rely on imports for almost everything. And these are some really critical elements for things like the defense industry, high-tech applications. So we've been working on developing and we finally have a finalized list of critical elements that we also find in acid mine drainage in addition to the rare earths. And they include cobalt, lithium, nickel, manganese, and zinc. So we add those to the value of the rare earth elements in putting together process streams and the economics behind this. We are right now in the process of building, and we've gotten great support from our West Virginia Department of Environmental Protection. And they have a land restoration division that is responsible for restoring former mine lands and also addressing water quality issues associated with those mine lands. So we've had, and they are, in one of their missions is to build a lot of treatment facilities to clean up watersheds and improve the quality of life in a lot of these rural communities that are otherwise devastated by these toxic streams. So what we've been doing is, with the Department of Environmental Protection, is working on ways to build the next generation of acid mine drainage treatment plants that incorporate rare earth and critical mineral recovery. So we are right now near completion of a plant near the town of Mount Storm, West Virginia, that will do just that. And it'll be a first of its kind. It'll be a 500 gallon per minute AMD treatment plant. AMD is acid mine drainage, with a rare earth concentrate recovery unit on the back end of it. So we will take they're treating it according to our specs. So we will take their concentrate and take it into our plant, dewater it, and further purify it. And then we have a product that we call a concentrate that we can then ship to a central facility for refining. And then, so the next step after that is to build the central refinery. So the United States doesn't have anything right now, any facility that can take rare earth concentrates and turn those into products like metals that our industry or defense agencies need. And so what we are looking forward to is a chance to design, build, operate a full-scale central refinery for the United States. Right now, there's only one mine in the U.S. that produces rare earth concentrates at all, and that's at Mountain Pass, California. It's on Interstate 15 between Los Angeles and San Bernardino, if you've ever been that way. If you're smart, you did it at night because it's really hot. So they ship all of their rare earth concentrates to China because only the Chinese, in this case, have the refining capacity to take those products. So obviously what we need in this country is our own refinery, and that's what we're hoping to help develop.
That's a really neat next step. I think it'll be such a cool evolution of this project to be able to take this, not only finding rare earth elements, processing them initially in the US, but also having that refining plant here to take them to the next step. So this project has moved along pretty quickly, it feels like. How were you able to get things moving forward this quickly from start to having a pilot operations running?
Well, one of the important things was involving the private sector early on in our technology development. And our first and foremost partner in that regard was Rockwell Automation. We knew that we would have to, in order to go from things that worked in a beaker to a full-scale commercial operation, we needed automations and controls and sensors. And so by bringing in Rockwell, they contributed to the project by providing us with a lot of those bits of equipment. And as a consequence, they've automated parts of our process train here in the laboratory. And then that same equipment is now moving up to our Mount Storm pilot plant. So it's a seamless move. It's already been demonstrated and tested at lab scale. And now we're ready for a pilot scale. But otherwise, most operations, most university-led research projects would just develop a project, make sure the chemistry is right, and then say, how do we make this work on a large scale in a continuous way that doesn't lose money? You don't want to wait 5 years to ask that question. And Rockwell has allowed us to answer a lot of those questions while we're developing the technology, which has been extremely helpful.
That's awesome. Sustainability is like written into our mission. It's something we care so deeply about. So we've been very thankful to be a part of this project. I learn a lot when I talk to you. Thank you very much for digging into what acid mine drainage is, how we're recovering rare earth elements. The work that you guys are doing at West Virginia University is just really incredible, and Rockwell is so happy to have our little part in it. We're really glad to partner with you on this. Thank you so much, Paul. And before we leave, could you recite the full periodic table for us, please?
Yes, I could. Hydrogen, helium. I'll do it in order of ascending atomic numbers. So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen,